Hi guys, I don't know if you can hear me. There's 13 of you in the room, so I'm going to let it sit for a little while. I'm going to talk around the subject. Hi Brian, you got to the live stream this time. Fantastic, excellent. Okay, so I just wanted to, whilst waiting for people to come into the room, to say it's very interesting that the Sapphire Group have announced that they have secured 8 times the funding they sought. I think they were looking for 250,000 to do certain work, and that they received 2 million. What is happening with the Vega project at the moment is that we have a vast amount to work through, and some extremely exciting things have happened in recent experiments, and they're not always obvious. You have to look at them and think about them and come back to them. But there's one that I hope to get out hopefully before the end of this week, which is really showing the kind of spiral sort of where you can imagine those Hessdalen lights where you've got a macro ball lightning like an Evo, and it hits the treetops and then it goes in this type of spiral. And this is quite a common thing. Now, obviously, there's a magnetic field in the Earth, and if you have an electrically charged particle and it's involved magnetism, you can end up with this kind of spiral going on. But it looks like we're seeing small spirals, and at least in one case or two, really rather large macro spirals, which are kind of akin to a sort of analog of what you would see in the Hessdalen lights. And so it's not just that, is that this video, what I need to do is I need to stabilize it, and I need to do, when I was doing animation, you would have these kind of like layers where you would have the previous layer would show through, so you could do the next layer. And so forth, so you could look out what they call the tweens, which is brief for in-betweens. Anyway, what I want to do is either in After Effects or Photoshop or whatever, I want to, every time one of these supposed EVOs comes out of the macro ball of fire, the technologically produced ball of fire, the what do you call it, ball of lightning, there are these things coming out, and you can see that certainly my first and second look at the video looks like they are following the field lines that are involved obviously in the overall reactor, but maybe predominantly the field lines of the macro ball lightning that's there. And so I want to trace those, and then you know, as the video plays, you can see, I don't know, but I'm seeing it in my head that you will see the field lines coming from the Evo, and it's just amazing that we're seeing this. And actually, Alan's here, and hi David. He shared with me some early analysis of a tungsten copper interaction in a CAN experiment that he's analysed on Alan Goldwater at Magic Sound on his scanning electron microscope. And we were discussing why it would occur, and it looks like you had the tungsten rod and you had the copper wire going round ostensibly to provide electricity to it, but you can imagine that the tungsten rapidly creates a tungsten oxide in there, so you get effectively a dielectric barrier between the tungsten electrode, which you want to pass the electrons into the water, it was the cathode in this case, and the copper that's attached to it. And obviously the copper's got very good conduction, but it doesn't like to oxidize. That's why it's a nobilish metal, and not on the level of platinum or gold or whatever, but it's still good at not oxidizing when compared to something like tungsten. And what I believe happening is something similar to what is happening in the Vega experiments, where we've been looking at this valley here. And what's happening with this valley is we had Henk put another sheet of, or a couple of sheets, and I've described this in another live stream, on top, and there was a crack there. What I believe is happening is effectively you've got a cathode and then another cathode, but there is a potential difference between them, albeit small, and there's a gap. And so if you take the corollary with what CAN has done, you've effectively got a dielectric barrier with the tungsten oxide, or at least a distinct change in conductivity, because actually tungsten's quite conductive by itself, and copper is very conductive, as we know. And it looks like that there are discharges going where the copper has a gap in a similar way to the brass plates that you've got in that cathode. And it looks like there's a real sense building that we can do some really interesting work by creating cavities between metals in the cathode on its way to the anode, and that these cavities may effectively act like in the Solon patent, where he has an electron beam and he's melting a low vapor pressure metal. He gets electron bunching, and the electron bunching leads to the coherence. That leads to the macro forming of in my view, coherent matter, or as Vladimir Vysotsky would say, coherent correlated states, like this. He just says that like 100 times in a presentation, and now I understand why. And he even refers to it with biological transmutations as well. So you hear these things and they sit in the back of your mind, and only when you see them and start to understand it can you be in a position to realize that they really know what they're talking about. And it just takes a long time. And on that note, at the beginning of the year, having been sent by Camilla Urbina a paper, I think it was on the 30th of December last year, I wrote to Sho in Japan and asked him to see if he could reach out to the University of Hokkaido to see if some of the unpublished papers and works of Takaaki Matsumoto could be liberated, as it were. And he wrote to them. He said, I'll do my best. And I talked about that in a different blog. And he had an answer back in supposedly a deceased person's hand, and so he's risen from the dead. And this is fantastic, because a lot of these researchers have learned from people like Henry Murray, from E.V. Gray, from Nikola Tesla, and from, in the case of Hutchison, he was working from Tesla, and then when Ken Shoulders came in, he was looking at the published works of obviously a range of people, but Winston Bostick and Nardi and so forth. And so it's important that these things are made public. And it dawned on me that there's probably so much important insight that Takaaki Matsumoto had seen that is not in the public domain, that could we find a way to get this out. Now, I've only done the briefest looking at this document, but I have seen some things in there already which I've not seen before, and some of those are from some things that are still yet to be published from, for instance, from our Project Omar analysis. And basically that's because last year, as we all know, was a bit of a non-starter. But anyway, actually, to be fair, one of the things that I hope to be able to show you today was published at ICCF 22 in the poster session, but you might blink it and miss it, because it's actually a composite of maybe 40 high-res SEM images, and it creates an image of what looks like the Nile Delta, where you can see that a plasmoid has come down from in the Indium, and it's done something rather special, and then it's just got something right at the end. And it's a thing right at the end which is very similar to something that Takaaki Matsumoto has observed. And there are other things, for instance, the hairs on the titanium, if you remember, where we loaded a titanium plate with a Marsa gas, and we got it so it was glowing, and then we touched it down on some Teflon plastic. Now, the reason I chose Teflon is a number of reasons. One, it has a low melting point. It starts to decay at about 330 degrees C. which obviously when you're frying and stuff, you hope to not get above that with the use of oil or whatever. But it kind of depolymerizes. But anyway, the Teflon also has fluorine in it, which has a high nuclear magnetic moment, and I believe is a very, very good LENR fuel. And I have also talked subsequently to my initial finding. But basically, in 2017, I had the webcam that I'm looking at this on. You're seeing the book on that webcam. I used with a modified piece of software to look for muons, and it's a piece of software called Cosmic Ray Finder, and I used that to look at echo fuel. But normally I would have thought to put black electrical insulating tape around it, but I couldn't find any. But what I could find was some polytetrafluoroethylene PTFE plumber's sealing tape, and I just put a very large amount of that around there, and you may have seen those images. Well, that's a piece of serendipity, because it was in the presentation of Yuri Bazhatov in Sochi. Sorry, it wasn't his presentation, but it was a presentation by Shishkin, where he said that Yuri Bazhatov was using fluoroplastics in to shield himself from the so-called strange radiation, or erzions, as he called them. And that I kind of clocked when I was there. And essentially what happened before Christmas is I was told, I was requested by principals in the Sapphire team, would I be happy to advise them on shielding and detection methods? And they said, and would you be happy to do that under an NDA? And I basically said, I'd be happy to help you, and you maybe could consider donating to the project, but I can't do it under an NDA, because I can't have exclusivity for someone with such important information. And so basically everyone has to know it at the same time. I haven't heard back from them. I do hope that they reach out, but the time has come, because whilst I've been warning Henk for a long time about the potentials of the strange radiation coming from his Vega experiments, he has only reported feeling strange when he's been around the reactor, and feels less strange after a period of time. And Dave has got his reactor up to speed now, and is starting to produce some interesting results. And he has a Geiger counter, not as good as this lovely Russian one that I have here. And if you want to get this Geiger counter, I would seriously recommend it. It's called a Radioscan 701. It has an OLED screen. It has actually an ARM Cortex in there, and it's regularly updated. It can run on rechargeable batteries. I think you can even recharge them in there. It does alpha, beta, gamma, and it's got internal logging as well as software logging and so forth, and you can power it by the data port there. Anyway, he hasn't got one as good as this, but he found that initially, when he got his thing up to speed, his Geiger Muller counter was going off scale when he was looking through his viewing port, and then after a period of time it was going off scale at from the metal from the reactor, the actual iron of the container. Now this is a real concern, and if you remember, I recorded Zatelepin talking to Parkhomov at Sochi, and if you go and look at that video, I think it's something like scientists that saved the world are trying to do it again, something like that. He is explaining that the strange radiation will accumulate in the metal, and then it'll radiate from the metal. And so it's now got to a point where there are technologies that are being put into commercial use, and I'm concerned that there isn't sufficient attention being paid to this. So I talk, and so basically I'm just, over the next week or two, I'm going to talk about ideas for detection. I've given you the one with the webcam. Yesterday I published a video on using the isotope of thallium. Now, this is not something I recommend generally people do. Thallium-205 is a high proportion of natural thallium. However, thallium in itself is extremely toxic and carcinogenic. You're more likely to die quickly from exposure to thallium than you are to strange radiation in a series of experiments. Although, if you have a high enough flux, according to Shishkin with his cavitator, you can kill yourself in about 1 hour, and that's nearly what Leclerc and his partner did at Nanospire. So, it depends on the flux coming from the reactor. But if you use thallium-205, this has been known for probably 40 years, certainly 35 years, that thallium-205, when it's fully ionized, it will beta decay. It'll self-beta decay, and it's a normally 100% stable atom. So thallium-205 will stay thallium-205 ordinarily as long as it's got its electrons until the end of time. But if you remove all of its electrons, it spits out an electron, which means it must have taken in a neutrino, because that's how it works. And therefore, it is effectively a neutrino detector. And the reality is they use this particular mineral that comes from Macedonia as a neutrino detector type for looking for the flux of solar neutrinos. And this has been suggested since even before 1985. So I proposed yesterday that because we are supposedly technologically producing cold neutrino clusters, and they're variously called different names, but the Russians like to call them string vortex solitons, which are a neutral form of magnetotoroelectrical radiation, and that these at least contain cold neutrinos in a condensate, and that they can also transport ions with them. Now, the point being is that if these things are interacting with the thallium in this, I think it's thallium arsenate sulfide or whatever. It's got a particular name, and if I did a blog on it yesterday. But basically, it produces lead-205, which doesn't occur in nature, okay? And lead-205 has a 15 million year half-life. Moreover, it can't do the electron capture that's necessary for it to do after that transition, because it's got no electrons available to the nucleus. Okay, so it's a near perfect isotope to be able to perform this. You're going from a high natural abundance thallium isotope to a non-existent natural abundance lead isotope, which has an extremely long half-life. And then what you do is you put that material into a mass spectrometer, and then you can see if that mass for the lead-205 is there, and if it is, that means we will have 100% proved the technological production of cold neutrinos. So if anyone wants to go out and win the Nobel Prize, right there is something that you can do. But you need to have the right kind of lab. This needs to be a lab that can handle thallium even in its chemical forms. This place in Macedonia, I think if you go and look it up, they say it's like the valley where nothing lives, because basically all life dies in this valley because the thallium is leaching out of this mineral. But it's quite a beautiful mineral, but I'm damned if I can find it. I think I would have to actually physically travel to Macedonia, which is not impossible, but it is difficult at the moment, and try and secure some of this. So this is not a simple thing, but it could be something that could prove this. There are some old collections you may be able to find some of this mineral in. Anyway, so that is another method, and I will share another method which is much safer to talk about that in the coming weeks. But I want to talk about the people that have suffered from this, that I personally had a relationship with, or by proxy. Then I want to talk about the shielding methods, and then I want to talk about the detection methods, and so forth, because I think Sapphire are doing the right thing. I've said for a number of years, in 2017, when I basically realized that this technology can rip matter apart, the most useful thing you can do until you know how to contain it is to use it to deal with nuclear waste. And there's plenty of that going around. There's like 80 years worth of it. And actually, this was a lifelong pursuit of Takaaki Matsumoto. So well before 1989, Takaaki Matsumoto was studying the potential technologies for dealing with nuclear waste, and this is for a very specific reason. Japan doesn't really have any hydrocarbons, useful to it, and much of its land is very loose and prone to earthquakes, as you probably well know. And this means that you don't have the opportunity to have wind farms and so on in the same way. And as you'll have seen from Texas this last week, you can have a whole area covered in wind farms, but then they could actually just break in an ice storm or snow, which you get in Japan as well. That's no good for solar. So they've been very heavily into nuclear as a means to power their economy. But of course, that builds up nuclear waste. So for the Japanese society, finding a solution to nuclear waste has been a very high priority in the nuclear industry, probably more so than almost anywhere else on Earth. And so it's something that I'm passionate about, and I know Sho, who helped me secure this book, is passionate about it. And I know Takaaki Matsumoto is passionate about it, and we're having some communication, and it looks like we might be able to get Matsumoto working with Dr. Ruishin Amaza, and actually get some traction on what's going on. And so when I was sent a couple of images of this book, I was extremely excited because in the index it was listing, I'd come up with a couple of months ago or a month and a half ago, because of what I'd seen in the Vega experiments, it looked like it was producing coherent matter. It turns out that a 2011 book on ball lightning that was subsequently sent to me says this is likely producing coherent matter, and that essentially it looked like that this would be able to do. The reason it was doing its transmutation is because it is cohering matter. And so I thought of a way to make a practical reactor using this technology. And then like the week and a half or whatever later, I get sent this page from the index, which is essentially saying that Takaaki Matsumoto is saying that. So I've only skimmed a few bits, but I want to talk about a little bit in the introduction. Then I want to go back to what I've just been talking about. And then I want to talk about some images that have never been shared before. At least I've not been able to find them on the web anywhere. There are papers in here that have not been disclosed before in a wide public forum. But specifically, there are images that speak to things that we have already observed in various technologies. So this is a science. We can get over the hurdle because we didn't know what he had seen. We found things that were interesting. We published them, and we keep finding that he's already seen them. So I'm going to read your comments now before I go forth. Okay, so... Hi, Lucas. To make a spaceship from home. Listen, I don't know if you're aware, but one of the only people, I'm speaking to Lucas's comment, one of the only people that has been able to replicate, even if it was just inadvertently, the work of John Hutchison, the effect, was Stoyan Sarkachev, and he had a coil around a ferrite rod, and he had some sparking going on there, and the ferrite rod bent, and that's not something a ferrite rod should do. It's brittle. It doesn't have a nice smooth curve in it. And actually, he said that if I can solve low energy nuclear reactions, he would give me and basically guide me through his field propulsion technology. And propulsion is more important actually than anti-gravity, because that allows you to travel in space. However, it's become very clear that this technology is related to the technology of low energy nuclear reactions. So I think we're on our way. Okay, so I'm trying to make a dielectric barrier setup. Okay, good. Yes, David, thallium is not good. This is something that for me, the thallium is something to categorically and unequivocally prove that low energy nuclear reaction processes are causing the transmutation via something that is like a neutrino. The interesting thing is not they're saying fully ionized, but if you can actually, they're actually using the mineral as a neutron detector, so neutrino detector rather, solar neutrino detector. So that in that case, I don't know whether they're fully ionizing, but it basically is infinitely more. I think the decay rate goes to basically it never decays for all eternity, but if you fully ionize it, it decays with a half-life of 47 days plus 5 or minus 4 days. So that is amazing. And in fact, actually, interestingly, in 1987, I shared this table, even tritium, if you fully ionize tritium, which is, well, basically 1 electron, I think it's 1.01, something like that. It does decay faster if you remove its electron. So that's something to think about. Yeah, I don't know how many different ways I can encourage Brilliant Light Power to take a look at their technology. As I say, I've been sharing with for their own safety with Henk and David potential ways to shield and detect, and I'm going to talk through those more precisely in the next week or so. Because we're very concerned that people might be inspired to start doing this experimenting, and I don't want them to end up like Ken Shoulders or like Norris Peary or like Farkash or like Yuji Bajatov. I don't want them to end up with some rapid onset cancer that is through their body. This needs to be respected. This technology is, from my point of view, it's all there is. It's the last great technology, and so but you are dealing with manipulating matter at its core level, and so it needs. And it's not that we don't live with this. It happens in the cavitation in a stream. It happens in lightning, and in fact. That's probably a good segue to what I will show you right now. So I'm just going to flick screens here, and then I'm just going to show something from the index of, or not the index, but the kind of like preface for the book here. And I think it's very important that we talk about that now. If maybe I can get this in view. Right, so it's going to be 2 frames. So I move my mugshot around. Get me out of the way. Right. So you can see here it's saying Discovery of Micro Ball Lightning BL. This is on page 19 of the book. Tiny shining sparks observed during underwater spark discharge experiments were discovered to be Itonic clusters, which were alternatively called micro ball lightning. Now, Itonic, he talked about this, I think, in 2000, actually in 1992, I think, that Itonic structures were positrons, electrons, and neutrinos, and they form a mesh web around the ions that they capture. Okay, so I'm now going to switch to the next page, which I think is really, really important to just run through, because it's his principal discoveries, and I think it's just amazing. It's just amazing. I tell you, if you are a scientist and you are interested in science, or not a scientist and interested in science, but you need to play safe. It needs to be playing safe. I can't say that enough. It's safety, 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 safety. Okay. There is so much low-hanging fruit with this technology. So much low-hanging fruit. It just boggles the mind. Okay, so I'm just going to get on with that. I was just astounded to I know every time I think about it, there's just so much low-hanging fruit. Okay, so let me see if I can get this in focus for you without shaking too much. Is that going to work? Right, I'm going to drag this down. Okay. Let me see if I can do this. Right. Hopefully you can see this as I read it. So Itonic clusters, sparks, were discovered to behave just like microball lightning. Itonic cluster sparks were discovered to have negative charges and magnetic moments. This is precisely what I've been saying for many years. It's what was shown in the plasmatron experiments in the 1970s and 80s in the Russian Plasma Physics Institute, but they didn't know what they were. And so here we go. We got negative charges and magnetic moments. And I'm adding to that the fact that they will always have magnetic moments. Right. A new kind of electric current was discovered as a flow of microball lightning. A new magnetic current was observed as a flow of microball lightning. Remember what I'm saying. What I believe here, now, bearing in mind I only just got this book today, I am telling you that in my view, what has caused this is a magnetic fluid. Okay, so rotational eruption was observed to occur from microball lightning, and we've shown that. And he has shown that in abundance. Microball lightning was discovered to be controlled with electric and magnetic fields. This is something that was clearly described by Ken Shoulders. He used penning traps, which are exactly this, a combination of electric and magnetic fields, so forth. So, electronuclear collapse suggested in natural and other technical fields. Electronuclear collapse was suggested to occur widely in natural and other technical fields. And this is something that Ken Shoulders said it is essentially ubiquitous. Microball lightning was discovered to be generated during earthquakes. Electronuclear collapse phenomena were suggested to occur during thunderstorms. Electronuclear collapse was suggested to occur during fission reactions, and so on. Now, I agree with that last one, and the evidence has been shown by the science team at Dubna. And if you go and look at Shishkin's 2018 Sochi presentation, he describes that from basically from gamma, I think Caesium 137 and other things. You actually get these birdies coming out, and I know John Hutchison had a very nice uranite sample, I think from Arabia, that he always had in his experiments. So he was always having some miniature ones of these coherent matter effectively coming out and interacting with his metals. So he had a start point. And you will know that probably, maybe you know that PAP had it initially in there as well. So the discoveries mentioned above would be very important to future physics as well as industries in the 21st century. Among them, the discovery of electronuclear collapse and electronuclear regeneration would be especially important because they meant that we opened the door to a super microscopic world of 10 to the power minus 33 centimeters at a stretch. Okay, so there we go. So that's a couple of things to look in, and I'm just going to have a look at. Okay, where are we at? Wow, you're talking a lot. Talk amongst yourselves. I'm just trying to catch up. Hi, Blues Doctor. Hi, Corky. I want to remind people that Tesla's 1932 drawing for the death ray had a dry steam vacuum, open-ended vacuum tube, and that he produced his electrical particles of matter from his cathode, which was either tungsten, is as a fed wire or mercury. So he was using a liquid cathode in 1932, and Ken Shoulder's patent also used a liquid cathode as well. In fact, he combined the ideas of Tesla, which was the tungsten. He had a tungsten tip, and then that was wetted with mercury. So he had the best of both worlds. It's like a self-healing electrode, because these things really do mess up electrodes. Cathode and the anode. Okay, so I might have to come back because I've got limited time. I've got so much I want to get through. So the first one is a little bit of a disappointment. Now, when I worked with Alexander Parkhomov to remake his book Space Earth Human here, and this was a very important part of my journey to do this. There was quite a bit he wanted to update, a few minor corrections and so forth. And so it really made sense after more than 10 years since the original Russian publication to do that. And what I will show you here is that this book here of Takaaki Matsumoto's is thick, is just as thick as this book, right? In fact, it's probably almost exactly the same, if not within the ballpark. And it has, what does it have? It has on its own, they're A4, and they're not the like more than double the size of the Parkhomov book, 289 pages. It is a big tome. However, that is not all of the story. When I was very excitedly looking at this to see if Takaaki Matsumoto had actually had the same idea to make a radiation remediation reactor along the same kind of lines as I had proposed in my one of my recent presentations. I went straight to the book to try and find roughly where it was in the book, and I couldn't find it. And so I'm gonna show you here a couple of slides, a couple of pages rather. Let me just go back here. Okay, so I was looking here. This one here, sprayer for radioactivity incineration with tiny ball lightning. Proceedings of the autumn meeting of Japan Atomic Energy Society, Sendai, and here. There's another series of ones, nuclear transmutation, incineration, collapse and regeneration by an electrical method. And lower down, he's got other ones along the same theme. And so I wanted to find those in the book, and I couldn't find them. And I got a bit concerned, so I thought I would go back to the index and see if there's any kind of referencing in there. And I don't know if you can see, but some of these, in fact, most of them have a hash by them. And down the bottom, I'll read this to you. Papers with a hash before the reference were admitted here due to the large volume and the high cost. They will be involved in a future edition with explanations for background of the study. So, the downside here is this is not a complete works. This, in fact, is, there are 84 presentations. You can see there 84, and only 26 are included in this book. Only 26. And the ones I really wanted to look at, not to say there isn't some amazing things that we're going to look at in a few minutes, it's just breathtaking to see what no one has discovered anything new. I'm absolutely convinced of this. And in fact, I think this whole, everything we're looking at here is ancient technology. That's by the by. And it's, as I've said since the beginning of 2017, it's eternal technology. In fact, all technology is eternal. You just haven't discovered it yet. It's always there for the taking, or for the so-called inventing. But this is something that will have been discovered over and over again. There's just no doubt about it, because it's just a basic natural phenomenon. It's not a design. It's not a design. This is the actual design of how things work. And so it will always have been discovered. And so let me just go back there. So what I've also noticed in the book is that I actually have some better images than the quality of the images produced in the book. So what I'm hoping to do is, as soon as possible, to work with Takaaki. And also some of these presentations that are not included in this book are actually in Japanese only. So there's multiple things. The ones that are already in the book, they need to be remastered. I need to try and find the best, or go to the original sources of the micrographs, the photographs, the SEM digital files if they're available, whatever, and remaster the book. I need to look at proofreading because there's often the papers need a little bit of proofreading. Then to get a philologist to work with me on the translation, and that might even be Sho. He's very capable, but it always needs quite a bit of work after that to do get the sense of what needs to be said right. So there's translation involved, and so what I'm saying is 20. I think it's 26 out of 84. So. This is only 1/3 of the materials. This is a lot of work, but I think it's incredibly important that this isn't reinvented. I think what he has done is clearly he got a lot of the low hanging fruit, I have to say, and with his toolbox that he is effectively established in the early 1990s. We will be able to terraform other planets. You'll be able to go to another planet, and I will describe in another presentation how it should allow you to achieve at least 0.8 the speed of light without even manipulating the vacuum. And that will allow us to get to Vega within a lifetime. So now you kind of maybe understand why various experiments in glowing action is called Vega, because it's another sun, but it's another sun that you can reach with this technology without even re-engineering the vacuum. But that's another story. But if you get there and you've got a habitable planet a planet in a habitable zone around a solar system, around a sun, but it doesn't have, for instance, carbon, and we all know carbon is extremely important for life, and the next alpha conjugate nuclei for carbon is oxygen, and oxygen is the most abundant element in the Earth's crust. And if you take 2 oxygens, you end up with sulfur. It's a very important element, and so forth. If you take 2 nitrogens, which obviously comes from the proton cycle with carbon, you can end up with two nitrogens fusing. That's 2 14s, goes to 28. That gives you silicon, oxygen. Basically, that's a large portion of the crust of the Earth. Now, by reorganizing nucleons like this, we will be able to terraform. And I'm not really wanting to get into what I've been calling this technology since the beginning of 2017, but you will be able to go and build worlds. You will be able to make uninhabitable rocks, as long as they, for instance, you would ideally want a liquid core. You would want that magnetic field. You would want it to have protection from its sun. And so forth. But if you didn't have the right elements there, you could use this technology to produce the energy to get there, to produce the energy to terraform, and to produce the energy to start life on another planet. So I cannot even begin to overstate the significance of what Matsumoto did. And I think it is existential that we ensure that his work is made available for people to not have to reinvent the wheel, because he was a nuclear scientist from the beginning in a country that wanted to study nuclear science. You know, we've had a situation here in the West where basically they made the bomb and virtually no one did nuclear science for the next 60 years. And I'm quoting Bill Gates saying that 10, 15, 20 years ago. So, you know, it's a great shame, but that wasn't the case in Japan. So we would have to live through 2 generations to get people to the level of where Takaaki Matsumoto who was quite a unique individual in that he was able to look at stuff and be able to discern what is actually interesting and then consider what could be the process that's causing that thing to happen. And he documented it. And it's just, it's a mind-boggling, crying shame that more attention wasn't paid to this work. But, it's published in the American Nuclear Society. It's published in fusion technology before they changed the rules. Anyway, I'm going to move on. I'm going to ask a couple of questions. So, okay. Lightsabers matter. They do. Lightsabers matter. But I'm probably going to interject another presentation that came out of something, but it's more to do about rock softening. But I think it's important to say that in the coming days. But anyway, I'm going to show you some things from the book in the end. And so what I did is as immediately I got it, I stopped what I planned to present today, and I started going through. And these have, to the best of my knowledge, never been disclosed before. So now the first thing is, let me see if I can get this in shot. Okay. Okay, so let me switch again. Get my mugshot out of the way. Right. So what you're looking at here is a sphere. Now, you might have heard me a few years ago saying, in Lena Systems, I'm just seeing spheres everywhere. I didn't know what they were at the time, but they're there. Anyway, so obviously a sphere is minimum surface area. It's a surface tension thing. So if you had something that was trying to squeeze an amount of matter into a minimum surface volume, it would be a sphere. So this is obviously something nature would do. And what you're looking at here is a lead sphere. Now, I don't know, because I've not read the papers associated with this. I might not even have the papers associated with the experiment that produced this sphere. But I do know why you would want to use lead as an electrode. And the reason is this, is that lead is the heaviest technically stable element. Bismuth has a very, very long half-life, but it is actually something that does naturally decay. It's not a fully stable element. But the isotopes of lead that you get in lead are fully stable, and we know from several different experiments, including from ECHO and so forth, that lead, and actually from Svyatamenko, and in fact I did a study on what is Lena anyway, or what is Lena fuel and stuff, and I showed that many different researchers observed the production of lead, and I've argued that the reason that is it's the last truly stable element. And what happens is that you get all this transmutation, and it just goes all the way to lead, and if it goes beyond lead, it just goes straight back to lead. So you end up with a lot of lead being produced. And so the interesting choice then would be, if it's an averaging function, what you see is if you're starting with a light element in an exotic vacuum object structure, or as he calls them, microball, lightning, or Itonic structures, and you get a heavy element, you get an averaging function. And I showed, using the Parkhomov calculator and about 50 seconds, that the elements that the alchemists were using for the last 5,000 years or whatever were exactly the elements you would use to have the most likely outcome of producing gold. So for instance, potassium, calcium, and quicksilver, which is mercury, lead and bismuth. These are the elements that would be most likely, most energetically favorable. Now, they produce all other kinds of other elements, but of the ones that could produce gold, they are most energetically favorable to produce gold, those combinations. So you get an averaging function if you've got light elements with heavy elements. And so essentially, if you've just got heavy elements and you do this, then if you're doing a discharge in water with, say, potassium, and you've got hydrogen and oxygen ions in there, then you have a potential for producing lighter elements, but you know you've got nothing in between. So if you see things in between, that becomes interesting. So anyway, this is, for instance, just a ball that comes out of it. Now, you might argue that this is just a melted ball, but what you're going to see in a few seconds is absolutely stunning. And for those that have been following this project, you will have seen something similar to this in recent years. Okay, let me do this. So there we go. What are we looking at there? We are looking at lead, and we have these whiskers, these fine fibers coming off the lead sphere. And these are actually lead fibers, okay? Now, we observed exactly these type of morphology of fibers coming from the titanium that was exposed to a Mars gas and then touched onto the polytetrafluoroethylene, the PTFE, in that explosion. If you remember, we got these, what Solin calls quantum coherent instant crystal formation. But on some of the crystals, there were these orthogonal, like magnetic and electric kind of arrangements of fibers coming off. And I believe that if Takaaki Matsumoto was to observe the base of these things, he would see heavier elements. But the problem is that he is starting with lead. So he's not going to see any heavier elements. What he would have done, in my view, is that if he had a high enough resolution, as we did at Madison, Wisconsin University, replicate what I observed at Magic Sound off that titanium. At the end of these fibers, he would have found a carbon nanotube. Okay, and in the case of the tungsten, titanium that had these fibers coming off from Project Omar. At the base, it had nickel, then it had iron, then it had chrome, and then it had titanium. And if you look at what's going on with that, at the base, you've got, I think, 3 alpha particles, then you've got 2 alpha particles, then you've got 1 alpha particle added to the titanium. And then after it runs out of titanium, it ends up by putting a carbon nanotube. So what you're saying, or what I was arguing, is that there is the metal that it started with, which is the titanium, and then it is loading into the titanium a number of alpha conjugates to produce the nickel, then the iron, then the chromium, and then when it's run out of an overabundance of carbon, it just lays down its balance of titanium that it has within it, and as it de-energizes it, it then just can end up with, by putting carbon nanotubes down until it completely runs out of alpha particles, other than 1 or 2. And if it puts 2 down, it puts down 8 beryllium, which decays immediately in whatever it is, 8 microseconds or something, very short time frame, to 2 alpha particles. Or if it has 1 alpha particle left over, it comes off as helium. And so that's what you get. And so the fact that he had lead, he would only see the fibers of lead. And in fact, he's seen this in a number of cases. And these are absolutely spectacular forms. They almost look like pollen. Now, I'm going to go later into the book, a step forward, because it's relevant, I think, at this point. So what you're seeing here is not the best image. It basically looks like a long hair on some basically on a big black frame. And this is one of the images that I would like to have a better quality of. But essentially what he's saying is that often you get these carbon nanotubes, and this is just, for me, it's wonderful because I came to the conclusion and have been saying for a good period of time now that this technology likes to form structures and conglomerates of structures that are all of the allotropes of carbon, be that diamond, graphite, and so forth. And so he is seeing a carbon fiber there. And we saw carbon fibers, carbon nanotubes being produced in the core of the Alexander Parkhomov 225-day reactor. And for the first time, I'm going to say that, and I kind of didn't, I thought this might be contamination, but it would appear that there has always been production of carbon nanotubes in the core of Lion reactors. And I have a whole presentation written years ago, and I've compared it to potential fibers that could have gone in there and so forth. But I wasn't confident enough to say that it was there. And when I saw the carbon nanotubes being formed in the reactor by Parkhomov that I presented at ICCF 22, and having just the week before observed carbon nanofibers being produced on the titanium as the last gasp of an EVO shedding its ionic load, I kind of thought, well, maybe that's true. And the interesting thing is, in this one, he's done a close-up. And this experiment isn't using lead, but what he found or it might have been, but anyway, this is the carbon fiber. But he found that there is a difference in elements, and you've got heavier elements like on the inside and so forth, and there's a distribution up to lighter elements on the outside, and then eventually carbon. So he has observed something already very similar to what we observed. I believe, and it's all the same thing. Now, there's something that I also want to share with you now, and what you might have seen me saying, and when you go back and look at these videos, there is these deposits on the outside here, and you will recognize from the videos where I've done the microscopy on that it looks like some sort of layer has been deposited on there. Now it is darker, and then other microball lightning has come out and it's interacted with that, and it's cleaned it back to the base layer, and it's balled up around the edges. And the question is, what is that? Well, we don't know. It could be lead that's coming out of the small amount of lead that's in the brass, because brass often does contain lead, and as I've already explained, lead doesn't like to transmute unless you've got a lot of light elements available, and it can average into the middle somewhere. If you have lead, that might be zinc, because zinc doesn't seem to be eaten so much, and we observed this in the Amasa gas treated 10 yen coin, where the copper seems to go, and that's highly conductive, and it also has two isotopes that have a magnetic moment. But zinc is different. It seems to get deposited behind. So could it be zinc? I don't know. But I'm so looking forward to doing the SEM, and I'm waiting to hear back from the party that may enable that. But if you look, let me just see if I can find this. Give me a second. I'm getting there slowly. Right, okay. Let me go back there. Okay. So what you're seeing here is on a metal plate, he has a film of carbon deposit. And here is a film of carbon deposit. I have to say, this looks quite like the deposit that is on the brass plate from the Vega experiment. So I am wondering if this is a carbon deposit that is on the top of that brass, and we shall see. But if so, we've replicated him again, and this does not surprise me. But we'll have to hold fire on making a conclusion on that, right? So then I want to find something else here. Okay, so the only way I can really do this justice is to actually show you what I'm referring to at the same time, kind of. So what you are looking at here is a Itonic cluster of carbon that's broken up. Okay, so it's like a splat mark, and you've got the outside here, and you can see these very particular type of crystal structures that have come from the breakup of this Itonic cluster of carbon. Now, the reason I was surprised when I saw this is, and if I can find it, I'm going to try and find it now. Bear with me. You can go and have a look at this in your own time, but it's in the monopole clutch presentation. And it's gone to an advert. Darn. Okay, so I'm going to see if I can just... Actually, it's probably best to just download the PDF. So what I'm looking at, and you can go and have a look at this at your end. I'm going to copy this into the chat window. I'm looking at this. In fact, I'll give you the point in the video where I'm at. It's at 15:14, so 9 seconds 9:14. So this is what I'm looking at here. And if I can pull this window up. Now I'm going to go to the slides, probably. Presentation slides, it's going to be easier. It's downloading it. Okay, so I'm going to try and add another window in here. Let's see if I can do this without breaking it. Talk amongst yourselves. If I had more time, I'd have prepared a shorter presentation. You'll get bored of me saying that soon. Up area. There we go. Well, that didn't work, did it? Okay. How can we do this? Why did that not work? Let me see if I can do it like this. Sorry. Well, that didn't work. Have a tea break. If you fast forwarded to this part of the video, I am trying to do something. Custom area, let's try that. Where's it gone? Where's it gone? No, not there. Okay. It just doesn't want me to do it. Okay, so anyway, the point is that it's not allowing me to do this, so I'm sorry. I don't know why. I'll see if I can get it to come up in a different window at some point. Let me try that. Okay. Desktop. That window. Yes, okay. I've got it in a different window here. So what I'm referring to here is this presentation, and maybe I can zoom into that. Can I zoom into that some way? Maybe I can go here and make that bigger. And can I go into there? Okay. So what I'm trying to draw your attention to here is this part on the Lion reactor. And it is the deposit that came on this corner in the metal bend. Now you've got this magnetohydrodynamic double structure here, and I kind of describe what I believe that is either before or after, I think later. But anyway, here we have this material here that's on the bend under the scanning electron microscope at Alan Goldwater's Magic Sound. And you can see that there are these crystals formed here. And if we go and find out what they are, they look like this, and they look surprisingly like the Itonic carbon that's fallen out. And it has a high proportion of carbon there. Now, the chromium, the iron, and potentially the silicon and the aluminium. So the aluminium, the chromium, and the iron come from the Cantal wire. The oxygen could just be largely on the surface, and you have the carbon coming out there. So, and also calcium is decalpha. Carbon is trialpha, oxygen is quad alpha, and calcium is decalpha, and you often see calcium being synthesized. So what I'm saying is that I believe that what he has observed there in that experiment here is very similar to what I am showing you here. And so I thought that was rather satisfying, and I would like to do some more analysis on that to find out whether that's the case and compare notes with him when that becomes a possibility. So that's that. And then, where is it? I'm going to show you one last thing, and then if I can find the image, I want to show you it to you, because it's just stunning, because it tells the whole story of a journey of an Evo and its final demise. So this is the cover slide image on this live broadcast. And so we are here. And what this is the breakup of the Itonic shell, the Itonic cluster, in an experiment. And you can see it has these kind of like petals that have come out. Now, if you actually look at the Itonic bead, it kind of has these geometric sections to it. And I guess that's just, it finds some mesh that balances what it's got inside it and stuff. I don't know, but maybe Takaaki Matsumoto's got a lot more to say about that. But I wanted to share something with you, so I'm going to find that on my other computer, and then we can talk through that. Okay. And I need to get it off. I'm trying on this one because I know better how to move around on the Mac. And I'm looking at, it's a very, very, very large image. And so give me a sec. Well, I'll see if you've got a question I can answer easy whilst I'm doing the work here of arranging this for viewing. Oh dear, now I've lost that. This is my epic fail part of the presentation. Okay, right. Okay, yes, Gordon, that is to the monopole clutch presentation. At some point, I will go through each of those slides and expand those out into full presentations. Hi, FB Angel. Hi, Gert. Hi, Rianderthal. Right, okay, so I'm going to dig this out, this image that I want to share with you. And I took this on Alan Goldwater's scanning electron microscope. And Alan Goldwater took a huge risk to buy a second-hand microscope from South Africa, and it took him quite a lot of time and heartache and effort and resources to get it operational. And it was only 3 years old, but it goes to show that you can buy a very nice tool and destroy it quite quickly. Not that he did, but he got it working again. And thanks to him and his initiative, that this was possible. So let me find that. The flower. Is it the flower? No. Yes. Not the whole thing. I don't know whether I have the whole thing here. No. Okay. I'm sorry, but this is tedious and I'm past curfew. So what I might do is do a separate video on this specific feature, but essentially what it was indium, and the Takaaki Matsumoto image that you saw that I just showed you, that kind of breaking up of an Itonic cluster, this one here, that is actually in Caesium. It's got a Caesium as the electrolyte, and it is the thick crust that's broken away there is the Itonic cluster of Caesium. And Caesium's interesting is because it is one isotope of 133. And in fact, alkaline metals were, and Caesium itself, including and also things like sodium, because sodium is only one isotope as well, 23. If you have the same atom, then you only have to get it at the same temperature and the same phase for it to cohere. And so the idea that cesium would cohere is not something that people who are doing cryogenic condensation have not experienced. The difference is that we are producing with ball lightning and microball lightning and itonic clusters is coherence at a different temperature. So I'm going to try again to find this, but the interesting point is that that experiment, which I showed the image of, or did I? I did show the image of, I think, on the title slide. That is actually also in cesium, in the electrolyte, but it's on an indium background. And the reason I chose indium is because indium is a very soft metal, and it also has a very high proportion of a beta isotope. And so that's specifically why I chose indium. And I will try and find it because it is just, it's so beautiful. So I need a very large image. Where is it? That might be, no. Okay. I don't know where that is immediately. Well, I found something else we can talk about just here, which I've shown before. So I will switch to that. This is what I was talking about earlier, and I need to have that in focus. So maybe I can get that to autofocus for me. Is it going to focus? Right. So what I was talking about were these whiskers that formed on this otherwise amorphous but beautiful crystal form, and you can see that the actual crystals themselves are multiply oriented, but in their own axis frame they are exactly 90 degrees, and then from those axes you have the 45 degrees of these fibers, and the fibers are coming out. And what we found is that they had this nickel titanium iron sort of step process, and this was verified independently by Madison, Wisconsin University. And so what I'm arguing is that if Matsumoto was to observe the end of the fibers on his lead itonic cluster decays, I believe that they would be carbon, as they were in the case of this titanium here. And I would suggest that if he was using lighter elements producing itonic decays, that the fibers that would be produced on there would have multiple isotopes, with the heaviest isotope being at the base on the parent matter. So that's one thing that I was talking about earlier, and I really want to show you this image because before I go. So just give me one more sec here. See if I can find it for you. No, I can't find it here immediately, but I will find it. And you get to look at my ugly mug for a few seconds longer. I'll have a look at your comments here. Okay, so many things to talk about. Anyway, I do have to go because it is curfew. So what I will say is that what I would like to do, and I'll take your view on this, if I can get permission to immediately remaster this book, then maybe that's an idea, because this is a tome all in itself. And it has, whilst it does have a lot of papers that you can actually get already online, it has some better quality images of the material in those, and in some cases not so good quality images, and it would be good to get the best quality and combine them into one document and so forth. And then it has a lot of material that has not been published, particularly these micrographs, which are spectacular. And here's another one that is interesting. This is another Iton cluster that's completely broken up, then it's fragmented and so forth. So maybe Alan Goldwater will like the look of this, and maybe Can will like the look of this, and maybe that is something that's going on the tungsten in his experiments. But that being said, what do people think? Do you think that I should focus on trying to get this one out to everyone first, or I mean, from my point of view, I think as soon as I can possibly get to Japan and work with him on capturing basically, I would say 70% of work or 65% of work that is not published in here, which involves a lot of the work that he has shared about how to use this technology to remediate nuclear waste. I think that probably would be very valuable to do. So I'd like to take an opinion on that. Okay, so if anyone's got any last questions, sorry about the disjointed end there, but I really wanted to show you something. But what I will do is I will try and come back tomorrow and just talk through that particular structure, because it's absolutely fantastic, because you see the plasmoid going up through a channel, and then it kind of like blows up, or something happens, and it goes out into a big fan, and it literally looks like the Nile Delta. And then it kind of like starts producing these very weird kind of structures and various different elements and glassy phase carbon and so forth. So it's quite interesting. And right at the top of that flower, I know I can show you just the top of the flower, not in the very high res, but I know where that is. So I will do that. Yeah, let me do that. Let me get this on shot. So, I'll make you feel drunk. Let me go there. So this is a glassy phase carbon structure, you can see, and this is part of it. There's various rubbish here. So this is oh God. I'm going to line up all the images together, and then I won't be going through text files. There we go. Okay. So It's not always one big image, and I'll go through it. But what you're seeing in this area is the channel which the plasmoid went up, and then some event happened here, and then it kind of divides up. You can see this is earlier part of the channel, and this is part where it kind of goes boom, and you have this structure here which is mostly carbon and nickel, and it has this kind of zigzag structure to it. It's very, very odd. So I've got it there in two different looks. There's another glassy carbon here and here. This is this glassy carbon I showed you before, but this is the flower just at the end, and I actually have 2 frames here, and this here is carbon, these 2 fingers here, and it's a vortex structure. So when these things blow up, they do produce these spiraling structures, and you can even see the spiraling function on here, but these are the parts that are folded out. And again, this is in Caesium electrolyte. And then you can see here, I've shifted the focal point on the SEM, so you can see the bit that sticks up. And here's another view of it, and these are some elements. And have I got any other? Yeah, so here's a larger view where the plasmoid comes up and it strikes here. So there's a division further down, somewhere further down. That occurs, and then you have something goes up here, fragment goes up here, goes up here, but something happens at this point, and this is the major event, and this is the tail end. So you've got the glassy bit here, and it comes out, and you have this structure which is similar to the structure that Matsumoto saw. But here's the overall structure. Now you might recognize something similar here. So you have this tail here, and then you have these 2 wings here. But this is you can see the delta here, and it's coming up here. And there's some major explosive event here where you get this nickel and carbon coming out of the main core. And maybe it might be the case that the steel in the Amasa plate, it maybe that contained nickel, I don't know, or at least it definitely had iron in there, and maybe nickel was synthesized from that by an alpha conjugate process. And you have this kind of like, almost looks like a liver here with muscle fibers. So you've got this explosion here, and it fans out here. But then you have the 2 cut halves here. So you have an explosion here, an explosion here, and then it goes all the way up here, and this is right on the end. That's where you see this bloom, and that's it. Looking at it in a different way, you can see this is the structure right on the end here, and there's a whole bunch of different elements in here. So this is a whole paper in itself, and there's an immense amount of work to do the analysis on here. But you can see it actually carved out a triangular section here, and then this whatever event here did this thing here. It did something else, but we're dealing with a science that there was a very big head start happen with Takeaki Matsumoto, and really no one should be starting from scratch. There's no excuse for it when this work has been done. So essentially, I'd like to say thank you for your time, and if you have any last questions before I shut down, like I say, I really want people's attention in the next week or so. Not necessarily so much with the next presentation I'm going to do on stone softening, but the presentation on detection and safety. And if you've got access to my remoteview.icu, the paper the presentation that I published yesterday on the use of thallium, and this really is only for people that can handle thallium without killing themselves, but thallium 205 really has the potential to prove categorically that the technological production of cold neutrinos in LENR systems. And so you could use this as a detector, and it's a passive detector because it accumulates, and then you take the accumulation of effect of cold neutrino fluxes, and then you put that into an ICP-MS, or you put it into a TOF-MS, and establish whether you've got the lead 205, that non-natural isotope of lead with a 15 million year half-life. Okay, so thank you, Brian, and it's really great that you managed to reach the presentation this time. And sorry, it's a bit disjointed. You know, when I do formal presentations, they're much more succinct. But I got this today, and I just wanted to share the excitement, the fact that yes, we've got some of this material in hand. Okay, so thank you very much. As ever, what I will try and do is I will try and go through your questions. Anything that I missed that I feel I should talk about, I will put into the associated article on remoteview.icu. I just want to shout out to Bido. Bido has helped get another tool, which I started to try today, which may give us better visuals of samples. And so I wanted to thank him. And he also supported the purchase of a optical spectrometer, which is on its way from California. I don't know when it will arrive, but I feel that I'm okay with running the supernova reactor now. I believe that I can shield myself sufficiently to respect the fact that I am a father, and run the experiments that I want to run there, and then get the resulting carbon onto the beamline in Lithuania. So that is that's going to cost about I think it's if I want to run 10 samples, it's going to cost $3,500 or something. It's about $300 a sample, but I think we can find that money. If people can help with that, that's great. And then once that work is done, I can return the supernova, because really I just need to prove that or at least not necessarily prove, but let's see if the carbon-14 in natural charcoal is able to decay by having the charcoal that's crushed, and then a sample of that split in two, and some of that run in the supernova reactor. And if that charcoal looks like it's 50,000 years old and it's only been in the supernova reactor for 3 minutes or whatever, then we know that we are causing carbon-14 to decay, its beta decay, and so we therefore know that it's likely some form of neutrinos are being formed in what Takaaki Matsumoto calls Itonic clusters, but micro ball lightning. And so this will be one proof which you could run every day of the week and to test this. And then what will happen is that the spectrometer, optical spectrometer, will then go to Henk, so that he, even before I get to work with him directly, can look to see if there are transmutations going on real time in his reactors. And this is actually something that the sadly departed Norris Peary did with his microwave reactor. He actually looked into he had a standard 2.45 gigahertz magnetron, and he had palladium, which he electrolytically loaded with deuterium, and then he put it in there, and it had an alumina inside. In fact, what I'm going to do as part of the safety awareness, I'm going to share the pictures, but I would encourage you to go to the SoundCloud if you don't know where that is. I will talk about that in the safety sort of walkthrough. But he was observing optical spectra of basically every element in the periodic table, and he's basically starting with palladium wire, deuterated electrolytically, and then exposed to a magnetron. That's it. Okay. So thank you very much for your time, and I will see you in the next video.